Hi guys, thanks for coming to our system design workshop. And then we'll be presenting with, I'm Eric, this is Andrew, and then also Jerry will be presenting the system design workshop. Before we get started, can we please take like 5 minutes to just fill out this attendance form? Alright guys, let's get started. So system design, as the name suggests, is just about designing the system. But the biggest reason as to why we need to learn this, apart from your own interest, is that many internships, as well as graduate programs, require system design interviews during the interview process. And then it's usually like in the middle, towards the end of the interview process, so like all the rounds and stuff. But yeah, and so for example, companies like TikTok, AWS, TikTok, and Optiva, they all ask a bunch of system design interviews. And this involves, going through case studies. For example, they will go through an application for you. They will give you some requirements, and then you have to fulfill those requirements by designing an architecture. So basically like a high-level view of what this application should look like in terms of the frameworks and stuff. However, what makes it challenging is that system design questions are usually very open-ended and abstract, and there's no one simple way to tackle everything, right? So, which is why we have to learn system design through case studies, and through experience, we'll get better at these. So, yeah. And I'm just gonna go through the movement, there's a camera. Yeah. So I'll just go through the agenda and what we're gonna learn throughout this lesson. In the beginning, we're gonna go through some introductory topics such as client-server requests and responses, to go through the basic paradigms in system design, as well as some introductory concepts of the requirements, for example, reliability, availability. And then we will proceed with a case study of the Messenger app by Meta. And we'll begin by identifying the requirements of it. And then next up, we'll actually design the system. So that includes like the high-level architecture, and then we'll actually discuss the technologies that we'll be implementing it with. So let's start with a client-server response. So something pretty simple, but just as an introduction, so it's basically just a fundamental paradigm in computing and models interactions between any two parties. So you have requests, which are requests for services, data, which could be data, and you also have responses, right? And it is the client that issues requests for services or data to the server, and then the server provides responses to the requests back. And sometimes the server might take a while to go through these requests and provide the responses, right? So the client might have to wait for a bit. Now, do you guys have any ideas on how a simple model like this might get a little more complicated than just one request and one response between the client and server? So anywhere where this can get a bit more complicated, anything where this can go wrong, yeah?
Multiple requests?
Yeah, exactly, right. So when there's multiple requests, what could be some issues that we have to work with?
Like queuing up and like losing, it's not being tracked.
Yeah, exactly, right. Then we have to introduce a queue and then raise conditions and stuff like that. And also about security. What if it's important, there's crucial information in the requests that are being issued, and we have to protect that, right? So we have to encrypt it and stuff like that. So that's some of the first stuff that we have to go through this workshop. So now I'll be handing over to Andrew on the actual concepts. Yeah.
Yeah. So this first thing we're going to talk about is something called non-functional requirements. When we talk about non-functional requirements, we're less interested in what the system does, but more interested in how the system does what it does. So that's things like reliability, right? Like if I have a system, what percentage of the time is it up and running? Whether that be like 99%, 99.9%, and so on. Another thing, like performance is another thing. So how fast is the system? What is the latency? What is the throughput? Those are some important questions that we need to consider. And another is scalability. So that's something like, how will the system respond to increased demand? Right? Like maybe I have, I don't know, like 2 users, just me and my other computer at the current moment. That's fine. Like my system handles that fine. But what happens when I have 1 million users, something like that? What do I have to change? How does the system respond? There's still a few other concepts.
You got it. I'll just do it.
So maintainability is another one. How easily can we add new features? How easily can we see where issues are and we can diagnose them in the system? We also have cost and efficiency. So how much is being spent to operate the system? You know, like if I have this many users, how much money am I spending like per request, per user, something like that. And also we have things like security. So how will we authenticate users, how we authorize them, et cetera, et cetera. So there are some other non-functional requirements, but they're not as like big, and we can talk about them a little later as well. Hand over to Jared. Okay. Oh, yeah.
Wait, sorry.
I'll just do
Yeah.
Just let me know.
Let me do it.
I'll do it.
All right. So in system design, it's very complicated. It's very, very abstract, and we need to follow a structure in order to step through the process logically. And especially, this also applies to if you're in an interview. It also applies to how the interviewer will assess you on your steps of thinking, your logical reasoning skills. So here are some steps that we will be following today to discuss this. First, we have functional requirements, right? So this is about what the user can actually do in an app. So for example, in Messenger, it's able to send a message, right? So in an interview, we could we actually need to ask all these questions. It's also a way for the interviewer to gauge how well you are able to consider all the requirements and anticipate the needs of the system, right? So what actions can the user perform? Secondly, after we know the actual features, we talk about the non-functional requirements, right? These can be both qualitative and quantitative, right? So things about reliability, availability, performance, things like that. And we'll go on to calculate some metrics. For example, how much data we'll actually need for the system. Right? We'll do some rough estimations on the magnitudes of the data we need, and then from there we can actually make our design considerations. Third, we're going to go through a high-level architecture. So what this means is a client-to-server architecture design would be stepping you through a diagram of how the client will respond to the server, how the server will respond to the client, and how the client will send through a request, and all the intermediate steps that the server needs to do in order to respond to that request. And then finally, we'll do a deep dive into the design and the technology. Later on, we'll emphasize that everything in system design is about trade-offs, right? Every technology, there's so many technologies out in the market, and we need to assess the pros and cons of each to the specific needs of our system. And so we'll be comparing technologies, exploring trade-offs, as I said, and doing design considerations. Sure. Step one is functional requirements, Kevin. Sorry. So, functional requirements describe the specific features and capabilities the system must provide to its users, right? And as we've talked about, like the Messenger app by Meta is extremely complex. It has a few, like, hundreds of thousands of people working there, and so we obviously can't go into all of that today, and neither are you required to in an interview. So we will be scoping the system down into a few functional requirements that we will actually be exploring, and because we only have 2 hours here as well. So we have first, and by the way, in an interview you need to be asking all of this. Some of these you can assume because they're very basic functions, but there are a lot of features that you need to, I guess, ask people, or ask the interviewer, hey, am I supposed to do this? Hey, is our system required to account for this, for example? So we have sending text, images, and videos, pretty standard functions. We have displaying read receipts. Yeah. We have push notifications. Yeah, and we have one-on-one messages, so direct messages, as well as group chats that we will be mostly covering in this lecture. Yeah, sure. Right, okay. So, non-functional requirements. As Andrew and Eric have mentioned before, these are the things like reliability, availability. So, can anyone think of any non-functional requirements for a messenger app in particular right now? As in, what does the messenger app need to prioritize?
Sending messages.
Okay. Yeah. So sending messages is a feature, right? And so, what do we need to send the messages fast? Do we need to send them reliably? Which one do you think we should focus on?
Or like fast.
Fast?
Yeah.
Right. Okay. Yeah. What if we lose messages? Is that good?
It's not good.
Yeah. So we probably want to prioritize reliability, right? Keep going.
Everything.
Availability, uptime, right? What if someone's in the hospital? You need to message people to pick them up. You don't want the message in the app to be down, right? So you need to be available. The messenger app needs to be available and up all the time. Third is latency, right? You don't want to send a message and then 5 minutes later Lucas gets it. Scalability. This is actually tied to how many users we want to be able to support. And in this case, it's always good to account for scalability, right? We're not going to be this, there's no point trying to define a system for just 100 people, because it's just not worth the time and money. Cost, speaking of money, we want to operate the system at a maintainable and sustainable cost level. And then finally, performance. So this is really vague. And we'll go into that a bit later, a bit deeper later on. Next one. Yeah. So we just talked about the qualitative, functional, non-functional requirements, and so in order to decide what technologies we want to use, there's often thresholds. For example, an SQL database, if there's more than 10 million entries, it will take roughly around 5 seconds. And so if we can gauge the magnitude of data we'll be able to we'll be storing, then we can make a more informed judgment on the technology that we'll use. And database was just one example. So yeah, keep going. Yeah. So we'll be assuming that our app has 1 million daily active users as a benchmark. This is not that much if we compare it to actual messengers like an Instagram or Messenger, but for convenience as well as manageability, we'll be doing that today. We'll also assume some other stats. Right? On average, 100 messages per user per day, 5 images per user per day, and half a video per user per day. And we'll also, so associated with each of these messages, videos, and images, we have relative sizes of data we need to store, right? A message we can assume is 20 characters long, and each character is a byte, and therefore we have 20 bytes. An image, this is very rough, but it's 100 kilobytes we'll assume for today, as well as a video being 3 megabytes. Obviously this depends and fluctuates depending on the quality and your system, but in a realistic interview, it doesn't really matter. So we'll be assuming that today. So we can move on to some calculations, right? Every user, if we have 100 messages per day, and every message is 20 bytes, that's 100 times 20 bytes, right? As you might have noticed, this is nothing compared to a video, which is 3 megabytes. So you can see here, if we have 0.5 videos per user per day, and then and each video is 3 megabytes, a megabyte is 10 to the 6 bytes, then we'll have roughly 2 megabytes per user per day. And then this is the metric we'll be assuming. So we've now discussed how much data we need per user per day. can any of you think of the next logical step to calculate in terms of how much data our system, our entire system will need? Yeah, again.
So like you multiply the the data that a user needs per day by the number of active users, like 1 million.
Yeah. Okay. And what is 1 million in the magnitude of 10? 10 to the
2 billion megabytes.
Sorry?
2 billion megabytes per day.
Yeah, 2 million megabytes per day, yeah, exactly. And 1 million is 10 to the 6, right? And megabyte is also 10 to the 6. So if we times that together, we have 2 to the power, 2 times 10 to the power of 12 megabytes per day. And that's 2 terabytes, right? So that's 2 terabytes per day we'll be storing. That's the messages we need to be storing. And then for a year, 365 days, that's very, very roughly 730 terabytes per year. Right? So this is a very, very rough calculation on how much data we'll need to store our system. And what you see here is completely an estimate. Some of them might not be accurate, but it doesn't really matter. The base stats doesn't really matter as long as we go through the actual thought process behind it and come to a logical conclusion. Yeah, so this is obviously going to carry into our storage and bandwidth sizing considerations. And next up, we'll move to some, architecture. Andrew?
Yeah. So, first thing, we'll just go through like a really basic example. So, and imagine we have like 2 users who are trying to communicate through this server. Well, we just have this really basic diagram of the users communicating through the server. But like, what are these arrows? What does it mean for them to like communicate with the server? Well, this is where we come to this thing called API design. So, okay, sure. Basically, we're looking at what we want to use for different parts of our system, like in this case, the users and the servers to communicate with each other. And when we do this, we want to think back to our requirements. We want to think back both non-functional and functional, and we want to think of the pros and cons of each technology that we could choose, and the trade-offs we are making when we are choosing any one technology over another, and what it is that we value the most for our specific use case, and that lets us choose the technology we want to use. So probably 4 of the most common ones, that you've probably heard of some of them, are firstly REST APIs. So what these give you are simple resource-based operations. So like put, post, get, delete, things like that. And then we have some other ones, for example, GraphQL. So what this essentially lets you do is pick precisely the fields of data that you want and not over or under fetch, like possibly in REST. So imagine I have some get method. Maybe it gives me a user ID, and let's say it gives me a user, and in that user there's like a user ID, there's some other information about the user. But let's say I only want like this guy's phone number. Well, I shouldn't really need to get everything else. Yep. Then we have WebSockets. So WebSockets are a way of communication which allows for bidirectional communication. So, for example, in like a REST system, we have a request from the user and a response, right? In WebSockets, we kind of have that as well, but we have this two-way thing where we can have sort of requests being made from the user, and also like things being from the server being told to the user as well. And also, it's low latency, and it's a persistent connection. Like, unless we go to close it, it'll stay open. Whereas something like a REST API, it's not persistent. It closes as soon as you send the information, and it's stateless. So unless we like specifically put state into the information which is being sent, it doesn't really remember. Like if I make one GET request, it doesn't remember the last GET request I made. whereas WebSockets, they have state. And then we have one other thing, so remote procedure calls. So this is essentially, let's say there's some function on some other server or like some other service, some other system, and we can make a request to that system to perform this function in a very, very high performance manner because it uses like binary encoding. And yeah, that's what it lets you do. But as we said, everything has like its pros and cons. So REST is like, it's easy to use, it's simple, it's very, very widespread, and you know, it's good for most things, but it does have this problem of over and under fetching. GraphQL, it seems like, well, okay, it just seems better than REST, but it's actually increases the complexity of your system a lot, and it can also be hard to cache because if each user can like, if people can pick out exactly what they want, well then not everyone's going to be picking out the same things. And this makes it hard to cache things, right? So WebSockets, so it's stateful. So that can be like a good thing and a bad thing. As we'll probably see later, this can introduce issues. And RPCs, well, if I'm using some function, it can be inflexible. So if we go back and take a look at our non-functional requirements, this is what our system needs to handle, right? What technology do you guys think would be suitable, well, most suitable, if you had to guess, for our messenger app? Does anyone have an idea? Yeah? WebSockets? Yeah, why is that?
Because it allows for bidirectional low latency communication.
Sure. And why exactly do we want that in our messenger app?
What if we want to make a video call?
Yeah, sure, yeah. So like, even just for messages, right? We don't want we can continuously receive the messages and we want them to be received quickly, right? And like, you know, we don't want to send the message and then 10 seconds later somebody gets the message, right? That's not good. So perhaps WebSockets is a good choice here. Yeah. So as was mentioned, there's a reason I put this pro here. It's very relevant to exactly what we're doing. It gives you bidirectional low latency exchange. Yeah. Okay. Sure.
All right. So we've gone through the functional and non-functional requirements here. And so I think it's time for us to start getting into our actual architecture and how we will be diagramming this system in terms of its components. As we can see here, this is a pretty simple diagram. It extended from just our user to server. Now we have a database, right, where we actually store text messages, images and videos and everything else. So what if the server goes down? Right? If you refer back to this diagram, if the server goes down, then we are out of options, right? Where's the API call going to go? Where is our latency and reliability, right? We have no uptime, and therefore we have a solution for this, and that is to simply make more servers, right? If we have more servers responding, think of them as like backups or they're working in a team, then if when this server goes down, yeah, keep going. Yeah. When one server goes down, we can route the API calls to other running servers, right? But how does this routing work, right? If we imagine here, we have like 3 servers here. How do we decide which call goes to which server, and ultimately which call gets like executed? And therefore, this is going to need something called a load balancer. Yeah, a load balancer. So we're going to show you a diagram of how this actually works now. If you want to keep... Oh, sorry, the slides are a bit messed up. Yeah, so look at our before image. So we have this server. We have these 3 servers now. We've replicated the central one, and then we added 2 more. And we have a load balancer that balances the API calls from our users, right? We can use as you can see on the second paragraph here, any load balancing algorithm to determine which server to direct traffic to, right? This is the job of the load balancer. So if you look at our load balancer, for example, user 1 makes a call, this might go to the top server, user 2 makes another call, this goes to the middle server, and then another call comes in and this gets distributed to the third server. And we can keep on going from server 1, 2, 3, from top to bottom, for each call we make sequentially, right? And so when a server dies, then the load balancer will, what actually happens is the load balancer will try to make a call, and then it will not see a response. And it'll show an internal error. And that's how you know the server is down or temporarily unavailable, right? So what the load balancer does is it now says, oh, the server is down now. We have just the 2 remaining servers, and every API call gets directed to either the 2 remaining ones now. And so that's how we handle, how we manage having high availability and high reliability of our service simply by making more servers. And you'll see a pattern that when something doesn't work, we probably just like make a copy of them, and that tends to work well. But there is something attached to this, which
I have a
is
question. So
yeah.
like with the previous one, because you're saying that with the load balancer, like
Yeah.
in that case, if a server's down, it would send the request, but then you already know that the server's down, so it bounces back, or how does? Because then like previously, right, if the server was down,
yeah.
before a load balancer was in place, how does that work? Doesn't it necessarily recognize that it's down?
Yeah, so this load balancer will try to send this API call again, right? So it depends on the implementation. Some modern systems use a timer, right? You expect that this load balancer gets a response from the server in, let's say, 10 milliseconds or something like that, right? And then if it doesn't, no matter, it assumes, if it doesn't receive that in 10 milliseconds, it assumes the server is down. And that's how it knows. But if there is a case where a network latency might just drop a packet or something when the server's not actually down and the timer is triggered regardless. And in this case, it's just a protocol, right? Then we can keep trying the server, and then if it doesn't work, then it definitely knows that this one is down. So there's a lot of implementation protocols, but for simplicity, we can assume that it sends a message, and after like a second, there's no response, then we assume it's down.
Right. So then, if there wasn't a load balancer and it was like a previous situation,
Yeah.
what would happen then? Like, we'll just consistently send it to that server that's down, or?
Yeah, so that would depend on how your application on the user side actually implements it, right? So if you just say, if we try to send a message and it doesn't work because the server is down,
Yeah.
then the message just gets lost basically, right? So you might have to manually type in to send another message.
Right. So then, in that case, the point of the load balancer is it redirects because like it's able to store it and like send it off.
Yes, yes.
Okay. Yeah.
And also, very importantly, for example, we have like 100 calls per second, right? If we have 100 calls per second and we only have one server, then that server is going to handle all 100 calls, right? So now we have 3 servers. Every server gets like 33 calls or something like that, right? So it manages the load in terms of the network traffic as well.
Okay. Thank you.
Yeah. So we have some trade-offs here in terms of availability. Right, let's go through them from left to right. So in terms of availability, we said previously there's a problem that if we only have one singular server and that server fails, we don't have anywhere to route the call to, right? So now we only have one load balancer with multiple servers. What if the load balancer fails? Does anyone have an idea to what we might do then? Yeah.
I mean, you could have like a backup load balancer.
Ooh, yeah. Good idea. Ooh, that's great. Yeah, we can, again, replicate load balancers. And so in modern architectures such as AWS or Azure, they provide load balancers, and so if a load balancer fails, they'll automatically scale another load balancer for you. And in practice, the modern systems will actually have multiple load balancers to balance these calls, and it's all abstracted away from you. Secondly, we have costs, right? Servers are expensive to maintain, and so and they're also expensive to buy. So if we have multiple servers, the costs will scale horizontally, and that might be a bit too expensive sometimes. And then we have scalability. if depending on our network traffic, we can either add or remove instances of service. This will help us manage the costs but then we have to monitor the traffic and then scale the service to the actual requirements of our traffic. So for example, in modern practices, we might have like peak traffic of messages is often at night, that's when people are texting. And so at night, we often have more load balancers as well as servers that are automatically scaled to manage traffic. And then during the night, for example, like 2 a.m., we might not get as many requests and messages, and therefore our system will be will automatically scale down these instances, and that's all abstracted away as well. And lastly, we have performance, right? With the addition of each server, the per node load reduces, and this decreases latency because the server simply has to process less things.
Wait, it's a question, right? So essentially, you're adding more servers, right?
Yeah.
But essentially, all the servers are still calling the same database, right?
Yes.
So doesn't that really not really solve the issue? Because now the database is still getting a lot of queries.
Yes.
Yes, you can have replica sets for the database.
Well, then won't
Yeah.
you have to sync won't you then have to sync the databases, which is another issue?
Yes. So, yeah, both of you are exactly right. If we have,
We read it from the primary and we sync from the primary to the rest.
yes.
Yeah.
Okay. Yeah. So what he's talking about, he's saying databases will encounter the exact same amount of traffic, regardless of how many servers we have, right? So to manage that, if a database cannot handle that much, we simply have more databases, right? But then if more databases, that comes with an issue, but because we need to sync these databases. So that is, we'll cover that actually in databases later on in the lecture. But the short answer to that is we have a main database, as you said, and every time the main database gets updated, we update the rest asynchronously. Any other questions?
Yeah, so like, what decides how many load balancers that are going to be in the system at the current time?
So a load balancer, the piece of technology usually have a specification, right? It can consume however many messages or however many kilobytes of data per second, right? So we actually look at the traffic that is needed. So for example, there's going to be 1,000 messages per second, 1,000 QPS as we say, and then if one load balancer can handle 100 QPS, then we need 10 of these load balancers, right? Otherwise the messages will keep building up, and then we'll eventually run out of space. Yeah, so we've talked about, going back to this problem, if we have a singular server and the server goes down, we are screwed, and one solution we talked about is simply adding more servers with a load balancer. Right? I'm going to introduce a second solution to you, which is using a message queue, right? And that message queue uses, is used for asynchronous updates, which we'll talk about. Cool. So, if you have a look at the diagram, it's basically the same as the load balancer, but instead, this arrow from the server, if it was a load balancer, then the load balancer directs the call to the server, right? If it's a message queue, then both the user and the server actually reads from the message queue. So what this message queue does, I'm going to call it MQ for short, is a queue that stores messages, right? Please note that I've wrapped the messages in quotation marks. And so, because what we're actually dealing with is a messenger system, and so these messages are not your literal messages. They are API calls and other requests that come in from the clients. Right? So this MQ we call, what does it do? Every MQ has two groups of people interacting with it. These groups are generalized into a producer, right? The users in this case, or the client, so maybe your phone. When you send a message, you publish/push a API call onto this message queue, right? And then what gets done is the consumer, which is our server, consumes and reads from the message queue and processes that request. So this is the general framework of a message queue. Does anyone have any questions for this one? Cool. again, we encounter a problem if the server goes offline. So when the server goes offline, the user keeps publishing/pushing to the message queue. And since the server is down, nothing gets actually consumed from the message queue, and so the load, the messages or the API requests gets built and built up. And when the server finally recovers, assuming it was a temporary temporary service availability, then when the server goes back online, then the consumption continues. So this actually is how we keep the reliability as well as the, actually just the reliability in check. Can anyone think of any issues when the server goes down? If we have a lot of requests from the users? Yeah.
Maybe like, maybe the messages will disappear, like they get lost.
Yeah. They could disappear. So message queue has inherent capacity attached to it, right? A message queue can, let's say, hold 1 million API requests. And so if that is full and we get more messages, it simply doesn't have the memory to hold it. And therefore, the messages will get lost. In order to prevent that, we also have another solution. Right? Here we have a singular server. Right? Here's a bit of a calculation we can do. If multiple users produce 10 tasks per second, right, and pushes to the message queue, and our server can only consume 5 tasks per second, then every second we have 5 extra messages that we can't consume. So over time, this builds up. And so, for example, our message queue can hold 100 messages, then this message queue will be filled in 20 seconds because we have net extra 5 tasks per second. And so, as we talked about earlier, our message queue will overfill, and that is not good because we lose messages. The solution, once again, is to have more servers, right? We call this a consumer group. And every server in the consumer group will consume from the same message queue, and will, so now we have 3 servers. We, again, distribute the load evenly, and now every, let's say again, our server can consume 5 tasks per second, then our server will be able to consume 15 tasks per second now, and that is how we handle, how we avoid the issue of overfilling the message queue. And so here, in usual industry practice, we will monitor our network traffic, see how many messages are pushed into the queue per second. We usually talk about peak traffic, so that's around 6 p.m. And we calculate how much messages are there per second, and then that's how we scale our servers. And that's how we figure out how many servers we actually need to prevent our message queue from overfilling. Any questions so far? Cool. Yeah, so we talked about peak traffic, right? 6 p.m., not that much, a lot of traffic, but 3 a.m., not that much traffic. And servers are expensive to run. So modern message queues, such as you might have heard Apache Kafka, it will let us dynamically scale our consumers, i.e. servers. This is a way to avoid wasting resources. 3 a.m., we don't want 100 servers running because there's nothing to consume. And yeah, that's a very nice quote about of modern technology, you can say.
What do you mean by dynamic?
Yeah, so we can have 100 servers at 6 p.m., but then we scale down, like dynamically scale down to 5 servers in like 2 a.m. Right? So we can constantly monitor how much traffic we have. If the QPS, the queries per second, go from 1,000 to 5, then we don't need that much servers, right? We can calculate how many servers we need.
So dynamically means you have to input a command to make it to scale, or
Yeah, basically. Yeah. You asynchronous, like you monitor, and then I guess that's your command. You monitor the traffic. Yeah.
Yeah, so like in relation to this with the case study or like an interview question, right? Do you have to talk about all of this when you're answering it?
Yes. So, do you remember what problem we were trying to solve with this?
The messenger thing?
Yeah. Like what exact problem? Because like it's when the server goes down, right?
Oh, yeah.
When the server goes down. So in an interview, you would talk about both practices, a message queue and a load balancer, and then we have trade-offs for each, right? For example, a message queue. One second. A message queue has lower costs, right? They're cheap to maintain. As we said, we can scale the consumers, and costs can scale. So that's the elasticity we talked about. Availability is guaranteed by elasticity, so we have as many servers as we need. Reliability, servers can go down with minimal loss of information. So yeah, like that's the whole point of the message queue, right? If a server goes down, or the message is not lost, it's still in the queue, and so we can consume it a bit later on. So messages are never lost, but they could be corrupted if the server was in the middle of consuming a message and it goes down somehow. And finally, latency. Do we think MQs are fast? Are they performant? No?
Wait,
Yeah.
so where is this message queue actually running on or stored?
Yeah. Message queues will be run on your cloud instances. You could have a computer or like a server rack. You could have a server rack for you that you've made, and then that could be hosting the application, which is the message queue. Like a message queue contains memory, right? Contains computational power. You can host that yourself, but in like nearly every day, people use AWS or other cloud infrastructure to host that thing.
How is that different from the server as well?
Which server are you talking about? Oh yeah, sorry. Well, like they're all computers at the end, right?
Yeah.
So a computer can have a computer can be built with a lot of memory for the message queue, or they can be built with a lot of CPU power for the server to handle. Does that make sense? Because everything is hardware, like if you boil it down, right? So yeah, does that answer your question?
Yeah.
And just to recap, a message queue is not that does not have much latency. Sorry, has very high latency comparatively to a load balancer, because it's in a queue and there are things before it that needs to be processed. So if we go, yeah. Which one do we choose?
I just wanted to ask, with like the message queue, like because you said it was dynamic, you're saying that it's sort of like preset, right? Because then you're saying that like during certain peak times, that's already historically the case. So you basically set it as that. But then, what if, for example, like there might be an instance where like someone they just all log in on a random time and it happens to be like during an off peak? Is there a way for them to know in that case, and then like in that case have all these servers up and running?
Yeah. So we're dealing with anomalies that we're not expecting, right?
Yeah, that's right.
And so in that case, depends on how good the system or / how good your load balancing server is. What we can expect is there are some messages that are lost. That definitely happens. And so the only thing we can ensure is that we could have extra servers on standby to account for these anomalies, and that comes with cost, right? Then you're having extra servers for potentially no reason at all, but you have to anticipate the need that there are unexpected traffic.
You can also have like systems that like they self-scale. So like let's say I'm at 100% capacity for some amount of time, then what it will do, it'll just create new instances on itself.
Oh right. So it's on the same server and it makes new
It'd be in the load balancing system. It's not necessarily like the same. It's not necessarily the same server. Yeah.
Oh, okay, right. So that's only for load balancers in that case. So for like message queues, like you won't have that case of scaling up.
Scaling up happens in almost every like technology here.
Yeah.
I chose message queue to cover scaling up because it seemed like a right place to do so. But in reality, load balancers also have scaling up and down servers.
Right. And then in that case, when you say like during off peaks, like you still have those servers, but then are they just like on sleep mode? Or like how do you describe it, right? Because then like you still have those servers, but then it's not being used, right? Like is that like on like?
Yeah.
Well, that's the thing. Like a lot of times these like you're using some sort of cloud service. Like you're essentially renting these this computing power from big companies like Amazon or like Google, right? You're just renting this, so like when you're not using it, like you can just give it back to them and they'll like rent it out to someone else.
Oh, okay.
And the cost is associated with how much you actually use.
Yeah. Okay, thank you.
Oh, yeah. Wait, actually, go back. So, yeah. Now we have to choose one between our load balancer and our message queue. For our messenger application, does anyone have any preferences / guesses which one they should use?
What happens if there's two requests to the load balancer? Will they be just hold like of the request and then you get queue for that?
Sorry, could you repeat that?
There's two requests to the load balancer.
Yeah.
How would it handle that?
So if there are multiple requests to the load balancer,
Yeah.
how would you distribute that?
Handle like if they were still at the same time. If it was a queue, they would put one in front of the other and then put it to the server.
Oh, okay. Yeah. I guess like in reality, the two requests are never going to be the exact same time, right? One might come from I don't know the US, and one might come from the Middle East, right? And so if we route that, it depends on the network as well. So we're saying when the API calls arrive at the actual load balancer, there's always going to be a prior and the other, right? Like the first and the second. And so the load balancer doesn't really care about like if they arrive nearly the same time. It only cares that, oh, look, it's we got one from user 1, then we go to this server. We got one from user 2, then we go to the second server. So I guess in that case, load balancer doesn't really care about the order. It treats every request as an independent request when it comes in, and then it also independently routes them.
So it just won't happen?
Yeah, it just won't happen. Yeah, that's the short. Yeah. Does anyone have any ideas which one we should use for our messenger?
Message queue?
Message queue? Yeah. Do you have any explanation?
It's not like we need the messages instantaneously, like we can wait half a second to be honest.
Yeah,
So that we don't lose our messages.
Yeah. Okay. Yeah, that's a really good point. So the biggest disadvantage about message queues is its latency, and the biggest disadvantage about load balancers is its unreliability, right? Yeah, so those are all really good considerations, and in practice we actually use both of them together. Yeah, so, but like we boil down to like simple concepts to explain. So in this case, we can have more servers in the load balancer just to make it more reliable, if that makes sense. So yeah, that's a good point as well. In an interview, you would ask which is your priority, right? Are you trying to prioritize cost, or are you trying to maximize the latency, or sorry, minimize the latency? So in this case, if we were to minimize the cost, then we'd be alright. We would be using a message queue. In the direction of this workshop, I've chosen a load balancer. But as we said, in reality, they're gonna. Yeah. So we refer back to actually make the decision. We refer back to our non-functional requirements. They have their pros and cons. Message MQs are more reliable, cost-effective, but it is slow for our purposes. And with more servers, horizontal scaling with a load balancer can achieve all of the above at the expense of cost. So let's assume here we don't really care about cost, and we just want to make everything as efficient as possible. So again, trade-offs, and we should definitely be discussing all of these things in the interview discussion. Right. So here is our updated system. Wait, okay. It should be a load balancer then. Ignore this. Where do we store our messages or images and videos, right? We use a database, as we mentioned before. There are different types of databases, and we need a way to choose them. In general, there are two types of databases. We have relational, which is SQL databases, as you might know, or we have non-relational databases, which is NoSQL. Yeah, so if you're not familiar with SQL, this is basically a representation of it. It's made up of these defined entities. Students have an ID and a name, courses have an ID and a name, and student courses have student IDs and course IDs. Right? They are the defined attributes, and importantly, in a relational databases, we can't change these. They're very rigid, and so it's basically like a table on Excel for your understanding. And we have no SQL, non-relational databases. Right? These it's any data structure that's not a table. Right? We could have documents, graphs, key value pairs, so hash maps, or we have white columns. Not sure what those are, but we have JSON files in general. And so these are used for very unstructured data, right? We have graphs and documents, and yeah. Let's talk about the differences between them. SQLs, as I mentioned, you need to define your table before you actually put them in, right? A student can definitely have a name and an ID, but it's really hard to change them. So this is what we talk about strong data integrity. You have to be very confident in your data's correctness. Data capacity is also limited. As we mentioned, as I said before, an SQL database, around 10 million entries will give you a 5-second query time. That is way too slow for some modern applications we need. So there are bypasses around it, but there is an inherent bottle cap in SQL databases. But it's really good at handling structured data. And an industry example is MySQL or PostgreSQL, as you might have heard before. NoSQL or non-relational databases are really good at handling unstructured and unpredictable data. Right? These things, these NoSQL databases, such as MongoDB, they prioritize performance and scalability. Yeah.
So you mentioned like API design before this, and you talk about GraphQL, like RPCs. Do they integrate with any of these sort of databases, or are they specific ones that you use?
Yes, good question. Yeah, so those API calls are simply how the client sends the message to the servers, right? The servers, it doesn't matter which API call it actually has. The servers just read these databases independently, fetch that information, and then return it in that API call format. So these sound related fields because they have intertwining data structures, but they're not actually related in terms of the end-to-end process. That makes sense? Yeah, and MongoDB and Redis is an example of NoSQL. Just to come back to databases, yeah. Let's do a little recap in case we forgot what's going on here. SQL is relational databases. Think of Excel sheets as SQL databases. They have strong data integrity, but they are quite slow when the data is, there's a lot of volume of data. And secondly, we have non-relational databases, and think of them as your JSON objects, right? They can be graphs, key map pairs, so hash maps, and they're good at handling unstructured, unpredictable data. Right? That's what our images and videos are, as well as text. So they have really good scalability and performance, and they're really good at so combining the first and second point, they're really good at handling large volumes of unstructured data, which is actually exactly what we have here. The example of this is MongoDB or Redis that you might be familiar with. So what do we use for our Messenger app? Does anyone want to throw out a guess? And it's actually, we're not limited to using one type of database. We can use multiple databases for different purposes. Anyone throw out a guess?
NoSQL.
Sorry? NoSQL? Yeah. What do we use to store NoSQL with? Sorry, what do we store NoSQL with? Yeah. Actually, first, what do we need to store?
The messages?
The messages, yeah. The images and the videos, right?
Yeah, that's fine.
Could anyone think of any other things we need to store?
User accounts.
User accounts, yeah. Anything else? We can relate that to our functional requirements. We have one-on-one VMs, group chats, read receipts, notifications, and the chat histories. So we would have something like a profile picture as well, as you said, user accounts, and also the relationships between between people, right? So are they friends? Are they blocked? Are they in a group chat together? So things like that. So turns out we actually use a combination of our relational and non-relational databases. Yeah. Good. As we said before, relationships, profile pictures, image, text, and videos, right? So we store the relationship between friends, group chats. So this is a very well-defined rigid relationship, right? We can easily use a relational database for this. We can store it in a table, and we can have different fields that are very defined, such as friends, not friends, blocked, and the status. Anyone have any questions/concerns with this? Does anyone think we can use a non-relational database for our relationships? For example, a graph. Yeah, so we could also use a NoSQL, non-relational database, with the nodes as people, as well as the edges as relationships. That's also a very delicate way of storing these. And so at the end, it's about discussing the possibilities, right? If there's no correct answer for this type of system design, and we want to explore both paths, especially in an interview or something like that. And we have next profile pictures, text, images, and videos. They are largely unstructured, right? They're usually stored in blobs, and we definitely use a non-relational database for this. Because we don't have a predefined structure to them, and there are a lot of these images and texts and videos, and therefore we want to be able to scale them. Whereas, for example, friends and group chats, there's only a limited amount of them, right? We said we have 1 million daily active users, and that's nowhere near our threshold. So something interesting we can do is so we have the profile pictures, the images in our NoSQL database, right? And we can store the address of that in the relational database. So in the relational database, we have a table with a field called profile pictures, right? And that's where we store user data, as you said. And so in that case, we were able to query the relational database for that user profile, and then we get the address of this profile picture, and then we query that address into the NoSQL database in very efficient time. Does anyone have any questions on this? Cool. So let's make we can make a final decision that we use a combination of NoSQL and SQL for this.
Yeah, so next thing we're going to talk about is, well, this problem. Imagine, like, just for argument's sake, that we have some server that's based in the US, and we have some user in Australia. What's the problem with this? Latency, right? Like, it takes time for this message to travel all the way across the internet from Australia to the US, and it's not a trivial amount of time. So, like, this distance means there's latency. And if you can imagine, let's say there's another user in Australia as well, right? What essentially has to happen is, for a message to be sent to user 2, user 1 has to communicate this with the server all the way in the US, and then the server in the US has to communicate this with user 2 all the way back in Australia. Clearly, this can't be optimal. So, like, one way we can solve this issue is we can use replicated servers in different geographic locations. And then another is we can use something called a content delivery network. Okay, so let's say one solution is we just have an Australian server, right? And the user just communicates with the Australian server. It's much closer. Clearly, this is faster, right? But running our own servers can be expensive, right? Running our own servers can be expensive, and let's say we had to service more places than just Australia, like Asia or Europe as well, right? Then we're going to need servers in all of these locations, and this can be very, very costly. So a solution to this is something called a content delivery network. So content delivery networks are basically just a bunch of servers that are geographically distributed over like across the globe, right? And this allows for faster communication with clients as they can be literally just closer to them. Yeah. So, well, like, who does this, right? Like, CDNs are really costly to maintain, like, because they're literally global. So big companies, so CDN providers are like Akamai, Cloudflare, Google, Amazon. Like all these companies, they have CDN services. And so when I request, like let's say one good example is some image, like let's say you can send GIFs, right, in your messaging app. But these GIFs are pretty much like the same for everyone, right? So what can be done is it can be stored in content delivery network, and we don't need to go all the way back to the original server or like whatever the server that like the main server is, and communicate with that. We can just fetch it straight from the content delivery network, and this will save us a lot of time, decrease latency a lot. So let's take a look at this model. So we claim that we can use the CDNs to deliver data like images, videos, chat history, profile pictures, etc. at a lower latency. And sort of what it looks like is this, is let's say I have some more authoritative server in the US, right? And it communicates with some CDN network, and all this CDN network is essentially a collection of CDN servers, a collection of servers, you can think of them as, that all communicate together and they transfer information between each other, right? And let's say one of these servers is in Europe and one of these servers is in Australia. This allows the Australian user to communicate with the CDN server that's in Australia and the European user to communicate with the CDN server that is in Europe. And we don't have to fetch certain information like the data that we've claimed here all the way back at the US server, which would take time. And you say like, well, like how much time is it really? Like it's only like, you know, maybe like 30 to 100 milliseconds, somewhere in that range. I don't remember exactly to communicate across the globe. But like this, all of this adds up. Like you say, oh, we can wait like half a second. But if you send a message in your messaging app, and even if it takes 1 second to send, it's like you get annoyed, right? Yeah. So that's the purpose of a CDN.
You want to talk about the home server?
Sorry.
Yeah.
Yeah. So.
Sure.
So the CDN server includes the whole architecture, which means the server database.
No, not necessarily.
Not necessarily.
Yeah. So there's certain communication that needs to happen between like some sort of more authoritative server and a server closer to the user, but like certain things like images and videos or like profile pictures, like specific to some users, like it can just be stored at a CDN server. And if it's like needed somewhere else, this is so there's one more thing I haven't quite mentioned, is like how does communication between CDN servers and like all servers, how does it happen? So actually there's two sort of like protocols ways. So we can have push and pull. So what happens is, let's say some information is communicated with the CDN server in Australia, like user one gives it some information. What it can then do is say, okay, I've received this new information, let me push it out to the rest of all the network. And this happens asynchronously, right? Or it can essentially say, well, let's say user one requests some information from the CDN server, and it can ask, let's say the US server, like our original server, well, I need this information. And this is a pool model. So it can also be that like every once in a while, like the CDN server requests information from the rest of the network, and pulls that information as well. So that would be part of the pool.
Synchronization, for example.
Sorry?
Synchronization, for example.
Synchronization is a problem?
No. I mean, how do you reduce the latency by this model?
How do you reduce latency? Well, because it's geographically closer to get information from this CDN server. Like the Australian one, for a user in Australia. Does that make sense?
I had a question. So, like, you're saying with this, like, the benefit of this is like information is like allocated to like the server that's closest to the user, or like, because then like, let's say you have someone from the US and then you're in Australia, right? If you want to send it through, then it would be the direct route, right? But then
if you were to send a message within your shop.
yeah, or like at least like the first part is like, how does it know which server to store it to? Like, is it more like as you were saying before that geographically, like you're figuring out where the user is and you store it, you try to allocate the data to be stored?
Yeah, it's based on geographic data. Like it'll try to find the closest thing, and that's partly to do with like the layer abstracted away by the CDN network. Yeah.
Right, because then like at least with this situation, right, you're saying that it'll be quicker because it goes through from the Europe CDN and it goes to the main one and it gets sent to Australia, right?
Sure.
Is that like saying like, let's say you're talking to someone in the US and the data's stored in Europe, or like, because like I'm just
If who is talking to who?
like let's say I'm in Australia and I'm talking to someone from the US, right?
Yeah.
Like right now, if you go from the US to Australia, it'll take you a long time. But then, like if you have it in Europe, it'll be quicker, right? So in that case, is their data stored in Europe then, or is it stored in the US, or like? Because I was just thinking. If
like let's say someone from the US sent a message to someone in Australia, right?
Yeah.
And we need to have this like chat history functionality, right?
Mm-hmm.
So we need to be able to retrieve chat history, right? What can happen is, well, the chat history, right, is then stored in some way in the Australian CDN server. So to fetch the history, we don't have to go, like, we don't have to contact the US server again. Like, if it's a completely new message, well, we can't just like create this. We don't know what the message is. We can't just create it out of thin air. We still have to, like, it still has to come from the original source. Like, if it was in the US. Does that make sense? If there was another user in the US communicating with the US server.
Because what you're saying is like for stuff like, instead of like, if it's something that you don't directly need to do to someone else, right, like sending a message or something like that, you're storing it locally at the user's geographical server, right?
Yeah.
But then like if it's for like larger ones, then there's only way is through a direct route, which is like to go to the US. Like you can't just say like
Larger. What do you mean by larger ones? Sorry.
like as in like if you're doing like, well, larger might not be the right word, but like if you're doing something where you're like, as I said, like a message where you have to interact with someone and like get them to like receive it, then the only way is to go through the US, right? Because that's a longer distance compared to having it.
Yeah. So you can also, like, in practice, there's a combination of like server replication and CDNs. So, like, you can imagine that even if it was sending like a new message, what would happen is we would have a replicated server in Australia, like something more like this. This is kind of a bad diagram, but let's say there was another user here, and then in addition to the CDN, there's also another server which the user can communicate with directly. And then it communicates with user 2, also in Australia. So we also avoid having to go back. Because it doesn't make sense that we're, like, 2 users in Australia are limited by the fact that we're hosting our server in the US.
Right, because then you're saying in that case there'll be 2 servers, one in the US and one in Australia, right?
Yep.
Because otherwise it's, okay.
So like in practice, it's a combination of, like pretty much everything we said, like in practice, you use a combination of everything because like you have a lot of like micro use cases with them, right?
Like,
Okay, yeah, that makes sense.
as you said, everything has like a problem, right? So, and every technology solves one problem, right? So in real life, we just combine everything, and then that like is inherently going to solve more problems, right? As long as you combine them correctly.
But of course, it also introduces more complexity. Yeah. Yeah, I'll talk about that. Yeah.
Wait, so what actually is the difference between like just having a server in the US and a server in Australia versus using like the CDN?
Versus using the CDN. Well,
Or is that literally what it is?
like the CDN doesn't necessarily contain the logic of your application, right?
Or it's just for stories?
It's just for storing stuff, right?
But isn't that what a server does as well?
I'm calling it a CDN. Like when I say server, it's like providing some service. In this case, the CDN server is providing the CDN service, whereas your server is providing your application service.
So what's the difference?
Like the logic of your messaging application, right? Like all of that stuff where you have to communicate with the database, etc., is in the logic of your application, right? Which is run by your application server. But the CDN server doesn't have that. It basically just allows you to retrieve past content, all common content.
Okay, I see.
Right.
Thank you.
Just think of CDNs as a local database.
Yeah.
Right.
It's a cache, basically. Yeah. We have some time, so one other thing we can talk about.
Ask them if anything, if they want to.
Right. Oh, first, wait, sure. Do we want to go to this final slide?
Sure.
Or you can do it, bro.
Yeah, so after everything, we have a final system here. This is very, 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 there's a lot of lines, a lot of things here. So we can walk through them, I guess, one by one. First, what it essentially is focus on the users, right? 2 users, and then the 3 servers, right? As we said, client, server, architecture. The server, the only thing the user knows is that it sends a message and the server responds back, right? This is the end-to-end flow, as we say, and there is a lot of things happening in the background. So first, we have a load balancer, right? As we said, this could be either a load balancer or a message queue. That is connected to the service, that's a load balancing service. And so now, back when Andrew mentioned API protocols, here we have a WebSocket between the edges to indicate the actual API protocol that we use here. That's connected to load balancers, that's connected to servers, right? Now, I will focus your attention on these 2, right? These databases we mentioned, NoSQL for storing images, videos, profile pictures, and texts. SQL databases can be used to store relationships between the 2, between people registered as well as user information, right? So server actually connects to these databases in a 2-way relationship, right? Server requests some information, and then that information gets back to the server. So this is sort of the interaction between the server and the actual databases. These are the main databases, right? As Andrew said before, we also have CDNs, content delivery networks, right? These content delivery networks, as I said, think of them as your local databases, right? In reality, there's more than one CDN here. We've sort of put it in a rectangle for you to like simplify it down, to abstract it down. But these CDNs are deployed everywhere in the world, depending on where your user is. And you can see an arrow from the CDN, an arrow from the server to the CDN, right? This means whenever a server writes to a database, it also writes to the CDN in a sense. And then the CDNs can actually fetch information from these NoSQL databases and SQL databases, because as we said, these are databases, right? And CDNs are also databases. So how do we keep them synchronized? Does anyone have any ideas? Yeah, so as Andrew said before, we have the pull and the push protocols, right? Whenever we write to a database, we can write straight to the CDNs around the world as a simplification. And whenever a CDN needs something, it can fetch the information from the database, because we know that these 2 databases will contain everything we need, right? And in reality, these databases will not just be singular points. There will be replications of each database, and likely a load balancer to determine which database handles whatever. Does anyone have any questions on this?
So the synchronization is happened automatically, or you have to implement in your.
Yeah. So I guess.
It should be I'm sorry. Atomic.
Atomic?
Yes.
Yeah, correct. So synchronization can happen either it happens automatically if we use like a CDN that's provided from like Google or Cloudflare. But like if we were to build the system from the ground up, we would have to implement it, right? And so, for example, when a server writes to the NoSQL database, right, then we can have either push or pull, and that means whether this database. So if it is if this database is in the pull protocol, in the push protocol, then this database will automatically write to the CDN, right? So that ensures every time information comes to the database, it will make sure that this goes to the CDN, and that's how you manage synchronization using the push protocol. Does that make sense?
Yes.
Okay, so what was I say? Yeah, and then the pull protocol is so there are some advantages of this. So for example, if a user looks at that CDN in their local geographic database, we are guaranteed mostly to always have that data, right? It is highly available, that data. But, so that's under the assumption that every time we write to this database, it writes to everything else, and that's under the push protocol. But if we have a pull protocol, that means this database, when it gets written to, nothing really happens, right? And then we look at that CDN, so we want some, like maybe a user's profile picture, and then we look at that CDN, and it's not guaranteed to consistent, right? What do? The CDN knows that, it's going to be, if that information exists, it's going to be in the main database. So what it does is it queries that information in the database here. So if that database is guaranteed to contain that information, and then when that query hits, it returns back, and then all the CDNs will have information of that knowledge from now on, right? So this is the same with, we talked about information coming into the database, but we also have updates, deletes from the database, and that is basically all the same thing. If something is deleted, then we will send that delete to the CDN, and vice versa. Does anyone have any other questions on this? And as a main point, we specified a load balancer between the users and the servers here, but in reality, I think every entity on this diagram will have a load balancer connected to them, and that's just how you manage like millions of users per day at a really large application.
You mean between servers and databases, there are load balancers?
Yes. So every arrow, there could be more complex features such as a message queue or a load balancer, probably both as well. Yeah. And that's all abstracted away by today's technology.
What are options for the load balancers at NGX?
When you say options, do you mean the types of load balancers?
Yeah. NGX is that.
Oh yeah.
Nginx.
Nginx.
Yeah. That's a load. Yeah. There are a lot of like gateways and things like that. There are tons of them.
Yeah, and I think the most important thing about a load balancer is its algorithm, right? How does it choose which server to direct the calls to? As I said, we have a round robin algorithm, which is that when an API call comes, it goes to this server, and it repeats itself, right? Yeah, and but you might want something called so basically, you direct that traffic to whichever server has the lowest rate right now. Yeah. So, for example, an API call might cost this server like a really long time, and might cost this server like and then this server gets another shorter API call, right? So that means this server is still working, but these two have already been served, has already finished processing. So that means our round robin algorithm might not work as well because like this API call has been is still processing, but these two have finished processing, and then the next call also goes to the server, right? That's not reasonable sometimes, and so we could have a load balancing algorithm that looks for these servers' availabilities, how busy they are, and then gives that new API call to the server that is the least busy. So there are tons of these algorithms out there. It's like an academic field.
JSQ.
Yeah. It's just like a scheduler, I think. Yeah.
Yeah, pretty much. So it's not like you might have like each server has its own queue, and essentially the load balancer sends the API calls to the server's queues, and what it can do is like say, this queue has a shorter length. There's less jobs in this queue. I'm just gonna send it to this queue, and maybe it chooses a heuristic like every time I'm gonna pick the server with the shortest queue and send that the next API call to that queue. Does that make sense? And actually, like, we haven't addressed this, but can anyone see an issue with having a load balancer with, let's say, a round robin algorithm and also using WebSockets? The issue is WebSockets like need to maintain a connection between like a certain user and a certain server. But how do we know that if we use a round robin algorithm or like some other algorithm that the load balancer sends requests from some user to the same server? Because let's say the connection is initiated between user 1 and let's call this server 1. Then the next time they try to communicate, the load balancer sends it to server 3. But server 3 has no idea what's actually like happening between user 1 and server 1, right?
So do they have
So like in this case, like realistically, you would have to have the load balancer have some sort of a ability to distribute the users to the same server but still equally. So like something like a consistent hash. So essentially like a hashing, like almost like if I have a hash map and I use a modular operation to always, let's say, map 7, the number 7 to the same slot. You would have something similar to that, right? Is there anything else we want to talk about? Yeah, I think that's.
Question.
I have a question. Like,
Oh, yeah.
This diagram, I'm trying to understand. Like, so then, like, you're saying that like, you got two users, and then like when they're like interacting, like maybe they send a message or something like that, which
Yeah.
goes to a WebSocket, and then it gets sent to a load balancer. And you're saying from there, then like depending on.
So actually, wait, that's kind of misleading. The WebSocket is technically between the user and the server, but yeah.
Oh, okay, right. Because it's like, because like the server contains like all the information, like the chat history and everything like that, or.
The server wouldn't contain it. The database would.
Oh, okay, right. So the database is the very end. So then, what does that server contain then?
The logic for essentially receiving API calls from the user or / load balancer, and how to store the data into databases.
Oh, okay, right. And then from there, so then the load balancer would send that request to the server, and then like what? And then like there's like a box around all the servers. Is that like a container or something?
Yeah.
Or?
It's just because we just wanted to like abstract away the server into like one thing that like the CDN interacts with, because in reality it's like many servers, right? And then the CDN itself is actually also many entities in itself. And the databases itself are also many different databases, right?
Okay. Because in that case, like there's an arrow, like there's a line connecting the server to the CDN.
Sure.
And like that's saying, is that like yeah, because like you guys talked about servers and CDNs before, right? And then like how like servers like they contain just like functionality, and like CDNs are like just like short-term memory.
Yeah.
So in that case, like these servers also like, because then in that case, like how does that work? So it communicates to the CDN, and then the CDN would send it to the database, right?
It depends. So what would happen is like it would send it to the CDN, and then like essentially what the CDN will have is like a version of the database somewhere, right? It has a version of the database somewhere.
Right. Okay. So that's why there's like
That really gets, so eventually the server communicates with the database.
Okay, so that's why like when you guys are talking like this is a combination, because then you've got the normal like relationship between the servers and the databases for like the red and black lines.
Yep.
But then you're saying that sometimes like it might be quicker to just do it for a CDN, which is why you've got another arrow. Like
Yes.
right. And then I just have a question with like the push and pull part.
Sure.
Where does that happen here again?
Well, it happens like sort of between the CDN and the databases essentially. Because remember, the database is multiple databases, right? And the CDN is multiple CDN like nodes, and they need to sync up the system, right?
Yeah.
So that's where it's happening between. Yes.
Okay, so you see that as just those lines are going.
Yeah, like this is really heavily abstracted. Like each of these lines is like a extremely complex thing.
Okay, yeah, thank you.
Yeah.
So for each request, you should fetch from the CDN first. If it is not there, then they will fetch from the database, and then they will push to the network, CDN network, so all the nodes.
Yeah, so if you don't find something, like if I don't find an image in the CDN, then I'll need to find it somewhere else.
So if it is not cached, the first time of the fetching will be slow, and after that, each fetch.
So like if you have a cache miss, then it will take a much longer time than if it's stored in the CDN and you have a hit.
Are the CDNs prioritized over the databases because they're closer geographically, or are they faster for other reasons?
Well, like CDNs themselves are just like databases in a way.
Yeah.
Yeah. So, like.
So as in they're
like they will contain replicas of databases.
So they're generally like closer than like a SQL and then.
Like if you had your own like authoritative database somewhere else, then like yeah, it would be faster if the information already exists in the CDN to just directly communicate with the CDN. Does that make sense? Yep. Any other questions? No? Oh, if that's all, thank you guys for coming. Really appreciate it. Yeah, thank you.